Hi again. My name is Harvey Molino, and this is the second in a series of little snippets from the G4, from the John M. Campbell G4 gas conditioning and processing section. And what I'm going to do today is talk to you about water and hydrates. In this particular chapter, what we discuss is the calculation of the water content of natural gas that is both sweet and sour. We also describe conditions that favor hydrate formation, and once we understand how hydrates are formed, we'll be able to figure out how to prevent them from occurring in a facility. We also, in this section, figure out how to estimate the hydrate formation temperature of a natural gas stream, and we take some time to calculate the amount of equilibrium hydrate inhibitor that one would need to inject in order to prevent hydrate formation in a pipeline. And we end up this session by comparing and contrasting the use of methanol and monoethylene glycol as equilibrium hydrate inhibitors. What I would like to do is to talk specifically about hydrate formation temperature in this particular segment. Going back to what we discussed when last we met, we talked about phase envelopes, and I've reconstructed the phase envelope on the screen. Overlaying that phase envelope, when you attend a G4 session, what we do is talk about calculating and locating the hydrate formation temperature curve. If you can keep your system operating to the on this side of the hydrate formation temperature, you will not form hydrates. However, if your system temperature is colder than the hydrate formation temperature, and if you have free water in your system, you run the danger of forming hydrates. So if you find yourself operating to the left of the hydrate formation temperature curve and you have free water in the system, you need to do something. One of the things that we discuss in this session is the calculation of the hydrate formation temperature. And I'd like to review with you an approach that we cover to figure out how to locate the hydrate formation temperature curve. The approach is called the Trekell-Campbell method, and what we do is we use charts in order to help us determine what the location of the hydrate formation temperature curve, where it may be. Here we see one chart that plots the mole percent of hydrocarbons versus a temperature displacement. And in the parameters are various components. We'll have normal butane, we'll have ethane, we have hydrogen sulfide, propane, and isobutane. Let's see how we can use this. This curve is specific for conditions of 69 bar or 1000 psia. And in the textbooks that you will receive at a G4 session, you will have curves that are somewhat different as your pressures increase. But we will take an example to show you how this curve is used. If you have a natural gas stream at 69 bar, and let's assume you have a composition, you have methane, ethane, propane, isobutane, normal butane, and C5 plus, and we'll make up a composition where you'll have 90 mole percent of methane, 3 mole percent of ethane, 3 mole percent of propane, 2 mole percent of isobutane, 1 mole percent of normal butane, and 1 mole percent of C5 plus. What we can do, given this composition and given this pressure of 69 bar, is we can figure out the hydrate formation temperature at this particular pressure. It all starts with the methane hydrate temperature formation. This is called a temperature displacement method. At each pressure, you will see a different value for the methane hydrate formation temperature. So let's start, because we're dealing with 69 bar, and we want to determine the hydrate formation temperature of this mixture. We will start by filling in the table. To do so, the methane hydrate formation temperature, which is given in the lower right-hand box, is 9.5 degrees Celsius. Now we want to add to that the contribution of ethane. Well, we have 3 mole percent ethane, so we find 3 mole percent over here, and we locate our ethane chart right over here. So we go in at 3 mole percent, we go up, and we read, about 1.6 degrees Celsius. That's the contribution that ethane makes to the hydrate formation temperature. So now we're going to take a look at the contribution of propane. Propane is 3 mole percent over here, and let's locate propane. Whoa! Look at that. Look at where propane is. Propane is all the way to the right on the curve. So we go all the way out over here, and we see that propane is going to contribute 4.8 degrees Celsius to the hydrate formation temperature. This is a key point. Watch your propane content when your wells change. You will typically have more propane in your gas than you will isobutane. So if your composition changes and your propane content increases, your hydrate formation temperature has just gone up. So be very careful about watching your propane content as wells come on and off in your facility. We can do the same thing with isobutane. Isobutane also is a big hydrate former, and with 2% isobutane, we go out to the isobutane curve, and we see that it contributes about 4.6 degrees to the hydrate formation temperature. We will do this for normal butane. Normal butane is 1%, and here's 1%. It's not a big number, and we end up with 0.2. And we find, and you will find when you attend a G4 session, that the C5 plus is actually a hydrate inhibitor. What it does is it subtracts the contribution, or lowers the contribution to the hydrate formation temperature, and in fact we end up with a negative number, negative 0.8. If you add all these numbers up, you will find the hydrate formation temperature of this particular mixture at 69 bar. I'll see you next time when we talk about energy changes in systems. Thank you for your time.